In class activity 17A, 1. When administering a drug, such as an anesthetic, it can be useful to have an accurate mathematical model of how the concentration of the drug changes in the body over time. One question that might be answered using this mathematical model might be, how long does it take for the anesthetic to take effect? What are some other questions that the model might help answer? You could say or ask how long before the anesthetic wears off, or how long will the drug stay in the bloodstream? Objectives for the activity. You will understand the values of a rational function for large values of the input may be approximated by using the leading terms in the numerator and denominator. A rational function may approach a finite value as its input becomes very large. You will be able to use the leading terms in the numerator and denominator of a rational function to predict the long-term behavior of the function. Use limit notation to describe the behavior of a rational function for large values of its input. Experiments show that the concentration in nanograms per milliliter of a certain anesthetic T hours after it is administered may be modeled by the function C1 of T equals 3000 T squared over the quantity T to the fourth plus 16. Use this function to answer questions 2 and 3. 2. In parts A and B, you will analyze the short-term behavior of the function C1 of T. Part A, the patient is considered to be under full sedation when the concentration of anesthetic is above 250 nanograms per milliliter. During what approximate time period is the patient under full sedation? So let's go ahead and there's different ways we could go approach this, but let's go here to our calculator. I entered the function in on the y1 line, and on y2 I put 250. So we'll get a horizontal line at 250, and we can look and see where these two graphs intersect, or where the y1 graph is above or below the y2 graph. So if we graph this, so we get a picture here, and we can say the patient is under full sedation between about, well, it's about not 1.25, not quite, but maybe 1.2. And again, not 3.25, not quite, but maybe 3.2. So between 1.2 and 3.2 after the anesthetic is administered. So let's go back here, and I'll just write this about 1.2 hours and 3.2 hours. About between 1.2 hours and 3.2 hours after the anesthetic is given. All right, let's go to part B. And since we're still in question 2, I'll leave question 2 at the top of the screen here. Part B says, at what time does the drug reach its maximum concentration? And what is this maximum concentration? So again, we can look at our graph to answer this question. And we're looking at the part of the graph that's above the horizontal line, y equals 250. So we're looking for the max there, and it looks like it reaches its max right at 2. So that would be 2 hours. So after 2 hours, we could say the drug reaches a maximum concentration, and the max that it reaches is 375. So let's go here and let's see. Okay. After 2 hours, it's an S, there we go, hours, the drug reaches its maximum concentration, and that maximum concentration is, we said 375. That would be There we go. Part 3. In this problem, you will analyze the long-term behavior of the function c sub 1 of t is equal to 3000 t squared over the quantity t to the fourth plus 16. Part A, it's not safe for the patient to drive until after the drug concentration falls below 20 nanograms per milliliter. How long should the patient wait before driving? Again, we can go to, look at our picture here of this, and it has to fall below 20 on the y-axis. So if we just keep scrolling, so it's gone beneath 25. So just roughly calculating, maybe about 20 over 12 hours, maybe 12 and a half hours. So let's go here and put it will take over 12 hours before, whoops, forgot my E, before the drug concentration falls to 20. 20 nanograms per milliliter. That's part A. Part B says, what value does the function approach for very large values of T? What does this mean in terms of the concentration of drug in the patient's body? So if we go back to the graph here, and we keep going farther and farther to the right, the positive x-axis, positive horizontal axis, we can see that the curve is approaching 0. So we're going up pretty far here. And so we're going to say that as t gets very large, the function c1 of t gets closer and closer to 0. So let's go back here. Okay. Scroll up just a little bit. There we go. Sometimes a treatment plan may require maintaining a steady concentration of a drug over an extended period of time. One way to achieve this is by administering the drug through an IV drip. Suppose that the resulting drug concentration from an IV drip is given by the function C2 of t equals 5000 t squared plus 450 t to the fourth over 3 t to the fourth plus 20, where the concentration C sub 2 is measured in nanograms per milliliter, and t is the number of hours after the IV drip is started. So, part 4, use the function C2 to answer the following questions. Part A, what is the maximum concentration that the drug reaches, and how, and when does this happen? Okay, so for part A, what's the maximum concentration? And when does this happen? I've graphed this here. I want to go to the y equals screen, and we graph this. And if we move this all the way to the top, we see the x is about 1.8, and the y is 406.3, roughly. And so that tells us that, let's go back to our picture here, or our paper here, and we can see that after about 1.8 hours, the drug reaches a maximum of about 406.3 nanograms per milliliter. For part B, what will the drug concentration in the bodies be after a long period of time? Okay, back to the graph after a long period of time. So we continue and continue. We can see that the curve is getting closer and closer to like 150. So let's take that and go back here and say as t gets large, c sub 2 of t gets closer and closer to 150. So the concentration, or the drug concentration, gets very close to 150 nanograms per milliliter. Part 5, let me scroll up here. It says, compare the equations for the functions C1 and C2. How might the leading terms in the numerator and denominator of these functions help you predict the values that each function approaches as t becomes very large? Well, the ratio of leading terms of C1, leading terms for C1 is 3000 t squared over t to the 4th. And we could even simplify this to just 3000 over t squared. Since the numerator is constant and the denominator is getting larger and larger, this function approaches 0 as t becomes very large. In C2, the ratio of leading terms is 450 t to the 4th over 3 t to the 4th, which we could write as 150. Which suggests that the function values will approach 150 after a long time. Limit notation is a compact way to describe the behavior of a function when its independent variable becomes large, to indicate that for very large values of t, the values of the function f get closer and closer to L. We write this notation: the limit of f of t as t approaches infinity is equal to capital L. This is read as the limit of f as t approaches infinity is equal to L. Part 6, consider the function c3 of t is equal to 15t squared plus 60t cubed plus 2t minus 10 over 10 minus 9t plus 36t cubed. Part A, it says find the limit of c3 as t approaches infinity. All right, so part A, it says find the limit of C3 as t approaches infinity. Well, concentrating on the leading terms, the numerator has 60t cubed. The denominator's term is 36t cubed. So we get rid of that and we reduce 60 over 36. We'll end up with 5/3, which is about 1.67 as a decimal. So as t gets, part B says, write a sentence describing the behavior of C. You could say as t gets larger and larger, C3 gets closer and closer to 5/3. Part 7, consider the function C4 listed here. Again, I'm going to look for the leading terms. It looks like the numerator is 20t squared, denominator is 2t cubed. So we'll get rid of that. And this will end up being 10 over t. And part B says write a sentence describing the behavior of C4. We can say for large values of t, C4 gets very close to 0. That's the end of this video. Take care.